Hey everybody, welcome to Supercoding Fun Time. This is the third episode. I'm your host, Eugene DePrince. I'm an associate professor at Florida State University in the Department of Chemistry and Biochemistry. And this stream is my effort, well, there's many reasons to do this. One, it's kind of an outreach activity to do some programming tutorials and help people learn how to do scientific programming. I want to do a combination of fun projects and quantum chemistry related projects because I'm a quantum chemist. Tonight I'm going to do a quantum chemistry focused project, which might explain why there's only 2 people here so far. But the 2 of us are going to have tons of fun. So please participate in the chat so I'm not all alone up here. Anyway, today I'm going to go through a tutorial for a little package that I put together that's called pdaggerq. It's meant for second-quantized operator string manipulation, and it has an accompanying tutorial that's on my website, chem.fsu.edu//deprince. You can find it under tutorials, and then there's creation and annihilation operators, normal order, and couple cluster theory. So basically we're going to follow this tutorial. I'm going to do a little bit of, not quite lecture, but I have some notes written out to try to explain some of these concepts if anyone's watching this who's more of a beginner in quantum chemistry and not an advanced graduate student or anything like that. Okay, so let's get started. I'm going to bring up a couple terminals. I hope I pull up the right ones. That's one of them. That's the other one. And I need my iPad, which is there. Okay. So everything I'm talking about today is related to second quantized formulations of quantum chemistry. So in second quantization, you can write down operators and wave functions in terms of sums over products of creation and annihilation operators. These are these little A hats with subscripts P and Q that I have here. And so, for example, you could write down the Hamiltonian operator for a many electron system as a sum of a 1 electron term and a 2 electron term, where the 1 electron operator has an A dagger and an A with the labels P and Q, and the 2 electron term has, there's a typo, nice. The 2 electron term has 2 annihilation operators and 2 creation operators. And I'm going to define these in greater detail below. And here, just so if you're not so familiar with what these symbols are, HPQ is something called a core Hamiltonian, and it's a sum of the integrals over kinetic energy and electron nuclear potential energy. And then the 2 electron term is this PRQS in rounded brackets. That's just the 2 electron repulsion integral. Okay, the key here, so I can write my operator in terms of sums over these creation and annihilation operators. And to understand these things, I don't know where my hats went. So A hat is something called an annihilation operator, and A hat sub P specifically will destroy an electron that lives in orbital P. And then I can use a shorthand for that that's just P hat or P, so I don't have to write A hats everywhere. And then A dagger is a creation operator. That's an operator that will create an electron in orbital Q, and I can use just a Q dagger as a shorthand for that. So here, if I have a product A dagger P, A Q, that moves an electron from orbital Q into orbital P. So that's a single electron transition operator. It just moves an electron. And so you can write any 1 electron operator like kinetic energy or electron nuclear attraction in terms of a sum over a 1 electron operator like this. And similarly, this is a 2 electron operator. It'll move 2 electrons from orbitals S and R into orbitals P and Q. Okay, how exciting. These operators encode some of the important properties of many electron wave functions, namely their anti-symmetry. So they have nice anti-commutation properties that preserve the anti-symmetry of a fermionic wave function. All that's encoded in these anti-commutation relations. So if I have any pair of these operators P and Q, PQ dagger plus Q dagger P dagger is equal to 0. Same with the annihilators, PQ plus QP is equal to 0. And then the really important one is when I have a mix of an annihilator and a creator, P dagger Q plus Q P dagger is delta PQ, where that's a Kronecker delta function. This where the name of the little package pdaggerq comes from that I'm going to be showing you how to use. Okay. Many body electronic structure methods are often formulated in terms of these second quantized operators because they give you a very compact way to write down the wave function, and they have these nice anti-commutation relations that encode the proper symmetry of the wave function. So for example, in coupled cluster theory, you could define a full wave function as a exponential operator e to the t, where this is, I'll define it, it's defined below, e to the t acting on some reference configuration that's probably from Hartree-Fock theory. And this t is defined in terms of sums over these creation and annihilation operators that I just introduced to you. So you have single electron transitions and two electron transitions with these two terms, and so forth. You can have up to n electron transitions if you have n electrons in your system. And here, convention in coupled cluster theory is generally that indices I and j, k, l, m, n all refer to orbitals that are occupied in this reference configuration, and a, b, c, d, e, f are virtual orbitals, so they're empty orbitals. They're empty orbitals in this configuration. So that's one example of where you can use creation and annihilation operators. Another is a kind of a funky class of methods that my group likes to work on that's based on something called a 2-electron reduced density matrix, or a 2-RDM. And here I can just demonstrate to you how the 2-RDM can be written in terms of creation and annihilation operators. If you take your electronic energy as an expectation value of the Hamiltonian, then you get two terms. Remember, I have my Hamiltonian up here that's defined in terms of these operators. I'm just going to take the expectation value of this. So if I scroll back down, when you take the expectation value, then you have this integral with psi star, psi integrated over all space, with the operator pdaggerq. That gives you this quantity that we call 1D. It's the one particle reduced density matrix. It's related to the probability of finding an electron somewhere in space. Okay, its eigenvalues are related to occupancies of orbitals. It's probability density. And this other piece with pdaggerq dagger SR is actually the definition of the 2-electron reduced density matrix, which is a pair probability density that tells you the probability of finding a pair of electrons. Well, it maps onto a conditional probability. If you have an electron here, what's the probability of also finding an electron here? Cool. So I can write these neat quantities in terms of creation and annihilation operators. So oftentimes, it's easiest to deal with these operators in working equations that we might code in a computer when they're written down in something that's called normal order. And I will define what that is. But first, I'll tell you that there's more than one way to define normal order. One way is normal order relative to something called a vacuum state that I will describe in a moment. And another is normal order relative to the Fermi vacuum, which is a Hartree-Fock reference state. Easy peasy. Okay, so normal order relative to a vacuum state. This is the way you can denote a vacuum state. It's a ket with nothing in it. So it's literally nothing. It's a vacuum. There's no occupied orbitals. Normal order, defined with respect to the vacuum state, is very simple. It's defined such that all of your annihilators lie to the right of all of your creators. And in this way, any normal ordered string of operators that acts on the vacuum state is going to give you 0. And you can see that because Q is an annihilator operator, so it's going to destroy an electron in orbital Q. Orbital Q is not occupied here, so the result of that operator acting on this function is 0. So because this is in normal order relative to the vacuum state, this string acting on the vacuum gives you 0. You can turn another operator that's not normal ordered into a normal ordered one by using those anti-commutation relations that I had a few pages up. So basically I can replace Q p dagger with delta pq minus p dagger q. And then if I wanted to know what q p dagger does to this vacuum state, I just replace it with this definition, and you get delta pq times the vacuum function minus p dagger q times the vacuum. This one's in normal order already, so I know that that result is 0. And that means I'm just left with delta pq times the vacuum. So this is a general property. And whenever you have a string of operators that are brought to normal order, the only ones that, I'll just read this. So the action of a string of operators on the vacuum state is trivial to determine. I just have to bring these operators to normal order. And then the only terms that are non-zero are the fully contracted, they're called fully contracted terms that involve no operators. So up here, I get one operator turns into two pieces. Only one of them has no operators in it, and that's the only term that survives. So that's the fully contracted term. Exciting. Okay, so that's the gist of how you define normal order relative to the true vacuum. In the 2RDM methods that I mentioned, specifically a variational family of 2RDM methods, I won't get into the details, but it becomes necessary to enforce constraints on the 2RDM that I introduced in order to guarantee that it corresponds to a real wave function. And we usually write down these conditions in terms of operator strings. So for example, at the level of two-particle n-representability conditions, which are called PQG, that doesn't really matter, we require 3 different RDMs to be positive semi-definite because they map onto probability densities. They should be positive quantities. All of their eigenvalues should be positive. So specifically, we require the 2RDM that I already introduced, the 2-hole RDM, and the particle hole RDM, all to be positive semi-definite. This 2-hole RDM maps onto a pair probability for not finding an electron and not finding an electron. And the particle hole RDM maps onto a pair probability for if I have an electron here, what's the probability of not having an electron somewhere else. All of these guys need to be positive semi-definite in order for the 2RDM to be meaningful. And all of these RDMs are related to each other, and we can derive relationships between them based on these commutator relations that I mentioned a while ago. So here, these are the definitions for the matrix elements associated with these operators. I have PQRS, as I already said. For the 2-hole matrix, I have PQ, S dagger, R dagger, so the daggers are in different spots. And same for G2, the daggers are just in different spots. And so I can relate G2 to D2 based on the commutator relations, as I said, which I can show you how to do here. So the gist of it is, all I need to do to map G2 to D2 is bring this operator string to normal order, and in RDM methods we use normal order with respect to the vacuum function, is how we think about our operators. So pdaggerq, S dagger R, I want to bring to normal order. So look, I left a blank spot in my notes so I can do that. This is pretty straightforward to do. You take this quantity of operators, pdaggerq, S dagger R, and I go through the string and find the first pair of operators that aren't in normal order, and I decide I want to switch these so I can use the anti-commutation relations. So I end up with p dagger delta qs minus S dagger q times R. So now there's 2 terms. So that's just equal to p dagger R delta qs minus p dagger S dagger qr. Okay, cool. So I bring this down here. That's equal to p dagger R, undo. Expectation value of p dagger R delta qs minus p dagger S dagger qr. And if you work out those 2 terms separately, you get 1d pr with a delta function minus 2d psrq. So you can map 2g pqrs onto the 1RDM and the 2RDM. So in those weird 2RDM based methods that my group likes to work on, oh, you can't see what I'm writing. So someone in the chat should tell me that if you're paying attention. If I wanted to constrain the proper relations between these RDMs, I would use this relationship that you can just derive in a very straightforward way from the anti-commutation relations for these operators. So this case was super easy to work out, but there are much more complicated cases to work out at higher particle levels. If I was worried about 3 particle terms or 4 particle terms. Nothing is complicated about this procedure. It's just tedious, which means it's perfect work for a computer if you can train a computer to rearrange these operators, which is really straightforward if you think about it, because all I did to turn this string into these two strings is march through one term at a time and check whether or not there are daggers and whether or not I have any terms without daggers to the left of terms with daggers. So the computer would just say, this is the wrong term. So I flip these two, add in a delta function, and split it into two different terms. And then the computer can analyze those two different terms and ask if they're in normal order. And that's it. It's perfect work for a computer, or a human if you have lots of time. So here, insert pdaggerq Python demo. So I'm going to show you how you do exactly this manipulation using some software that my group produced. Let me see, how do I pull this up? So I'll go to the GitHub page for this code. It's GitHub, my username's edaprince3, and pdaggerq is the code. It's public, so you can download it and play with it. There's tons of instructions, not really instructions, but some details on what different terms mean. I can go through that in a little bit. But first I'll just show you this super simple example. Let me pull up my windows again. I really only need one window, so let's just do this with one window. Okay, so I want to first clone this repository. And hallelujah, my internet works. It must be working if I'm streaming. So there I have pdaggerq. Here's a whole bunch of C files. All of the code for manipulating the operator strings are written in these C++ files. The actual interface is in Python, and I'll show you that in a moment. So the first thing we need to do is compile. All you need is CMake to compile this. I don't even remember what version of CMake. You can check. CMake dot is enough to get this compiled. Okay, it's configured. Make. It compiles easy enough. It makes my head hurt when the line breaks like that, so let's do that. And now I can, there's a samples directory here, so you can check out all sorts of samples for doing evaluating energies at the couple cluster level of theory, or density matrices at the configuration interaction level of theory, or at the equation of motion couple cluster level of theory. There's lots of samples here. We're going to start with making a new sample completely from scratch, and I'm going to map that G2 matrix to the 2RDM. So the first thing I need to do is pull up my cheat sheet on my other computer here so that this goes smoothly. I need to tell Python where this library lives. I have no idea why this is so ugly, but it doesn't matter. So the first thing I'm going to do is tell Python where to look. Please don't ask me what any of this stuff means, because I don't know Python. Okay, so that tells it where to find the library, and then I can import it. And then the first thing I need to do is create an a-hat object, which is the operator string manipulator. A-hat, get it? Like a creation operator, or an annihilation operator. So a-hat I'm going to get from pdaggerq, and I'm going to call some helper class. And that helper class takes an argument as a string, and that argument tells you if you're looking at the true vacuum or the Fermi vacuum. So I want the true vacuum. And then I can set bra and ket states if I want. They're set automatically to the vacuum state by default, I think. So I don't need to worry about that. So I'm not actually going to do that. And then I can set a print level. So I can make sure I see what's going on in the guts of the code. Sure, I can print what I'm doing. So I'm going to print out G2, oops, the pdaggerq element. And the way I do that, I can use a simple function that's called setString. So that sets a string of creation and annihilation operators. And I'm going to set it to be the operators that correspond to these labels. So I have, it's going to be listed as a vector of strings. So my first operator is I star. I don't have a character for dagger, so I just used star. And then J without a star. And then L star. And then K. And this, you have to remember that the last two labels get flipped when you're defining the operators. So that's my operator string. You could set other things like stuff you want to multiply the operator string against. There are certain letters we can't use right. So you can use any letter you want. There are some letters that are used internally by the code. So actually M and N and E and F are used internally by the code if you're setting the bra state. I need to make that more flexible. And then, as I'll explain in a moment, when you when you're dealing with the Fermi vacuum instead of the true vacuum, anytime you have a general sum, you have to split it into sums over occupied and virtual labels. So the code internally will turn a P, which is a general label, into like O1 and V1. And then it would turn Q into O2 and V2. So you wouldn't want to use those labels, but they're very silly looking labels anyway that you probably wouldn't want to use. It's pretty safe if you wanted to call all occupied labels I with a number afterwards, that would be perfectly fine. So I1, I2, I3. All virtual labels could be A1, A2, A3, so forth. That's probably the safest thing to do. Actually, the last bug I fixed in this code was based on assumptions the code was making about what orbital labels were used internally versus externally. This code is by no means perfect. That's why it's free. If you have problems with it, just let me know. I'd be happy to help you. Okay, so I set the string. Like I said, there's a whole bunch of attributes you could set. So the string actually isn't added to be manipulated until I say add new string. So I could also add factors. I could add tensors that it should be multiplied against. That will make more sense in a moment. But for this, all I need is this naked string of creation and annihilation operators. Okay, and then the way you bring it to normal, so you could do this with as many strings as you wanted. Add new string, add new string, add new string, and it would just create a list of these, and then once you want to simplify everything, you would say simplify. And for some reason that looks like it's off the screen a little bit, so let me pull that over. Okay, so right, when I want to simplify things, let me bring my cheat sheet back up, because I got confused with the chat. A hat dot simplify, and then that'll bring everything to normal order with respect to the true vacuum here, and then I can print. And then you could use this class again to generate different normal ordered strings, but you'd have to clear your result first, so a hat dot clear. That's not necessary if you're not doing anything else, but I'm just putting it there so you know that it exists. That's it. So that's how you would manipulate G2. So here I just need to say Python. I think that you need Python 3 to run this code. Python g2.py. And look at that. So it prints out, I'm doing G2. Here's my starting string. There's the factor I mentioned, a +1. And I have I star j, L star k. And that rearranges to ik delta jl minus I dagger L dagger JK. Now, I think I just realized that my example I did used P's and Q's and R's and S's. So let me redo this real quick with the right labels so I can show you that you get the correct result. So this is pdaggerq, pdaggerq, S dagger R. Yeah, and is that how I defined it here? pdaggerq, S dagger R, yes. Enter. And what do I get? I get a D1 term, pdagger R, times delta QS minus pdagger S dagger QR. Why is that the wrong order? What did I do wrong here? How embarrassing. Did I put it in the wrong order in the input file? Help me, chat. Well, this does not inspire much confidence in the quality of this code, does it? Yeah, the last two switched. So did I mess that up? Oh yeah, I'm so dumb. Yes. Thank you. So that's pdagger, qdagger, pdagger, sdagger, rq would be the operator. So that's exactly what I have here. So that's right. Whew. That caused me to perspire. That was a close one. Entangled AF, thank you for the win. Okay. That's a great username, by the way. So that's the gist of it. It may seem like a lot of work to write this little code, but I guarantee you when you have a complicated string, it's much easier to do it with a computer than by hand. Okay, moving on. So this case was really easy to work out, but everything becomes much more tedious at higher particle levels. As I said, perfect work for a computer. We did the demo. How great. So now that's basically all I want to say about the normal order version of things. And I want to switch to thinking about, the true vacuum version of things. I want to think about normal order relative to the Fermi vacuum. So in addition to this one example where I was using the operator string manipulation to map different RDMs to one another, the most useful scenario for a normal order code like this is to evaluate integrals over really large strings of second quantized operators that show up in many body methods, like couple cluster theory, that I already mentioned to you guys. So if I do a couple cluster wave function and limit it to just double excitations, I have a wave function that's e to the t2. It's just the 2-electron operator t, acting on the Hartree-Fock reference. T2 is given by a sum over all possible double excitations, so from all orbitals ij into AB. And this factor of a fourth just accounts for double counting because you could have ij or ji, and that results in electrons out of the same pair of orbitals. Okay, so you have the Schrodinger equation, h psi equals e psi. If I put in my wave function ansatz here, I have h e t times psi 0 times the Hartree-Fock term e t2 times the Hartree-Fock term. In couple cluster theory, you don't variationally minimize the energy. You use a projective solution to the equations, which means that you basically will left multiply everything you've got by e to the minus t2. And that has the nice convenient property that the exponentials go away on the right-hand side. And so if I then take this equation and left multiply by the reference configuration and integrate over all space, then I get this. I have an integral over this operator product e to the minus t, h e to the t. That's equal to the energy. So now the question is, how in the world do you evaluate this crazy-looking operator product? Sounds like Chinese. I don't speak Chinese, so I wouldn't know that. Sounds like quantum chemistry. So anyway, how do you evaluate something like this? There's a very nice expansion, well-known expansion called the Baker-Campbell-Hausdorff expansion, or BCH, that says you can write a similarity transformed operator like this. That's what this is called, where you have e to the minus t, h e to the t. You can write this similarity transformed Hamiltonian as a bunch of commutators involving the operator that's in the exponent. So you get the operator itself, the operator commutator with the thing in the exponent, the operator double commutator with the thing in the exponent, and I lost a hat, very important. Then you have 1 over 3 factorial triple commutator, and so forth. And in principle, this sum goes on forever. But couple cluster theory has the really nice property that this series naturally truncates after only 4 commutators. So you get a very complicated but nice finite set of equations that you'd have to evaluate. But if you look at this thing, you note, oh my gosh, here I have a product of 4 different two-body operators. So I'm going to have a gazillion. I I lost a bunch of hats. I think I just added them. I hope I got them all. Anyway, you're going to have a ton of operators to rearrange, so I don't want to do that by hand. I have no interest in doing that by hand. Okay, so let's do that with pdaggerq and see what happens. So we have our energy is given by the expectation value of this similarity transform Hamiltonian, where the expectation value is taken with respect to the reference configuration. And it turns out, if you're only Mr. Coop, thank you, I've got them all. I would like to hang with you, Mr. Coop. Anyway, if you're just looking at the energy, it turns out anything after the single commutator ends up being 0. So that simplifies what we have to do here. You'd have 3 terms, term just involving the operator, and then 2 terms that come from the commutator. So that guy is just the reference energy, the Hartree-Fock energy. So that's easy. I'm done with that. Now we have these 2 terms to contend with. This one looks complicated. I have my T2, so I have a 1/4 sum over these 4 labels, this 2-body operator, and then the Hamiltonian, and then my amplitudes, the T amplitudes. So if I look at this guy, though, I have an A dagger right next to my reference configuration. And it turns out that, what does E stand for? It's the energy. It's the electronic energy. Capital E is the electronic energy. So here, I started way back up here with the Schrodinger equation. H psi is E psi. So this is the total electronic energy. If you're familiar with coupled cluster theory, this is not the correlation energy. This is the total electronic energy. Okay, so then scroll up, scroll up, scroll up. I have this term from this guy. I have an A dagger next to a reference configuration. And it turns out a creator, you can think about it acting to the left on this bra state. That looks like an annihilator acting on a ket. In other words, this guy looks like A times the reference with a dagger. A times the reference. The reference has only orbitals that are occupied in the occupied configuration, in the Hartree-Fock configuration. A is a virtual orbital. So if I try to destroy an electron in a virtual orbital, the result of that is 0. So I know that this guy, bra times A hat, dagger, is going to be 0 for that reason. So that also simplifies things. That means this entire term is 0. I don't have to even think about it. So that leaves me with this guy. So I know that's the reference energy. This is another piece that I have yet to evaluate. Oh, here it is. It's just those 2 terms. I can expand this guy in terms of the operators, H and T2. And now I have a double sum. I have a sum over my T amplitudes, and I have a sum over my 2 electron integrals, the labels of the 2 electron integral tensor, PQ, R, and S. If you write that down in terms of these tensors, you have T, IJAB, and PRQS. And then you have this god-awful string of operators to deal with. P dagger, Q dagger, SR, A dagger, B dagger, JI. Okay. I could evaluate this by bringing all these operators to normal order. And only the fully contracted terms would survive. So that's easy enough. That's nice, except in this case, this isn't the true vacuum. It's the Hartree-Fock reference configuration. Totally not Eugene. Is this a college class? This is actually like a tutorial that I'm meaning to do for my group at Florida State University. That's a quantum chemistry method development group. I have a whole bunch of tutorials on my website. So part of why I'm doing this is for them. Part of why I'm doing this is to have the tutorial on my website. Yeah, this is material that would show up in a graduate level quantum chemistry class. Okay, great question. Okay, so anyway, I could evaluate this by bringing everything to normal order, but there's a problem, and that's that this isn't the vacuum state. This is the Hartree-Fock state. So it's not empty. There's a whole bunch of orbitals that are occupied in it, and I have to worry about those. And I can't tell. I'm watching the stream here, and it keeps freezing, so I don't know if I'm freezing or if it's just that. Sorry. Okay. I failed physics in high school, so I'm very confused. Sorry. We could just tell jokes. I like telling jokes. I never liked physics in high school anyway. I never liked physics in college either. And then I did chemistry, and it turns out I like doing theoretical chemistry, which ended up being physics. Who knew? Okay, so there's two problems with the fact that this is the Hartree-Fock configuration. The first is that I have to worry about all of the creators that are involved in defining that configuration. So this is another mistake. I have a product of all these creators on this reference configuration. So I have to worry about all of these operators when I'm worrying about normal order. That's the second problem. Okay, so the string's much larger than just H and T. The second problem is this string of operators depends on the system you're looking at. I'm glad I'm back. Sorry, I don't know, I have crappy internet and I'm using Wi-Fi on my computer. And I think my wife's watching TV downstairs. It's a perfect storm. Anyway, this operator is also system dependent. So if you were doing a calculation for a water molecule or H2 or a protein, there'd be a different number of strings here operators to worry about. So it just complicates things. And it turns out you can simplify things by change how we define what normal order is. So instead of defining normal order relative to the vacuum state, we're going to define it relative to the Fermi vacuum. And that's the Hartree-Fock reference state. So the rules are pretty simple. They're not as simple as they were for the vacuum state, but they're simple nonetheless. The first rule is any operator that annihilates the reference is called an annihilator. So that could be either a creator in the occupied space. I can't create an electron in an orbital that's already occupied. That would violate Pauli exclusion principle. So that's 0. So that's an annihilator. And then also my annihilator can't annihilate an electron that doesn't exist. So if this is an empty orbital in this configuration, this is going to be 0. So then we call both I dagger and A annihilators. All operators that don't annihilate the reference state are called creators. So this A dagger creates an electron in the virtual orbital A. That's fine. The result is not 0. And this product, this I, destroys an occupied orbital I in this configuration. So that's also not 0. So these are both designated as creators. With these new definitions, normal order is defined the same way as it is in for the true vacuum state, and that's just that all creators have to be to the left of all annihilators. So that's fine. There's just it just makes things more tedious, because anytime you have a general sum, like what would show up in the Hamiltonian or any other general one or two body operator, a general sum has to be broken into sums over both occupied and virtual labels. So that just gives you gazillions of more terms than you would normally have to deal with. I guess it's like a conservation of complexity. If you were working with the true vacuum, you'd have to worry about all the extra electrons used to build the Fermi vacuum. In this case, you have to worry about breaking up these silly sums. So here's a really simple example, or straightforward example. If I have this one electron operator that I had at the very beginning of all of this, a sum over P and Q, this operator pdaggerq, and this matrix element HPQ. P and Q are general labels. If I want to evaluate this integral in using the Fermi vacuum as a reference, I have to split both the sum over P and the sum over Q into sums over occupied and virtual labels. So I'd split that into where P and Q are both occupied, I and J, where one of them is occupied and the other one isn't, vice versa, one of them is not occupied, the other one is, and then both unoccupied. And you can already see some of these terms end up being 0. A acting on the reference gives you 0, because that's an annihilator. A dagger acting this way also gives you 0, because if I act in that to the left, I can think of that as acting to the right as an annihilator. And then this guy is also 0, because B acting on this part is 0. So you're only left with this first term. So I have that whole sum I had above is just this one term, one sum. You can't see both occupied. Oh, I'm sorry. So the problem is I have the screen cut off on my monitor. So I see more when I'm looking down. So thank you. Just keep telling me when that happens. Okay, so anyway, these are your 4 terms. 3 of them go away, and the entire sum just becomes this one guy. And now I can bring this to normal order with respect to the Fermi vacuum. That means I want all creators to the left of annihilators. So that means I need to bring J to the left of I dagger. So I dagger J is delta Ij minus J I dagger. And now that comes from the anti-commutation relations 20 minutes ago. Now I have 2 terms. This guy splits into 2 terms. And I have Hij with this delta function minus this other term, which is 0, because it's been brought to normal order. This delta function is just a constant. It can come out of this integral. And so I have the overlap of the Hartree-Fock reference with itself. If it's normalized, that's just 1. And so now I have a sum involving a delta function. Delta functions gobble labels. So I end up with a sum over only I, Hii. So using the idea of normal order in the Fermi vacuum, we can, in just 1 page, show that this sum of integrals over these operators is just equal to a sum of these matrix elements, Hii. It's pretty straightforward. It was really tedious, but it wasn't too complicated to do once you know the rules. How fun. 10 people here. How about that? Probably half of you are my group, I hope. Well, I hope more than my group is here. That came out wrong. Okay, so that was just a little aside to show you how you bring things to normal order with the Fermi vacuum. Now, oh, Ask a Scientist Gaming is here. Wow. I am honored. Thanks for coming. I'm sure you're loving this and how accessible it is. Probably. Okay, now back to couple cluster theory. I had 3 terms. I argued that one of them is 0, so I just had 2 terms. I have the reference energy, and then, oh, Calm Down Bronco is here too! What a night. This is fantastic. Okay. I have the reference energy, and then this sum, it was the Hamiltonian times T2. And the Hamiltonian had 2 pieces. It has this 2-electron piece and this 1-electron piece. So I have this absolutely horrendous looking operator string to deal with. And 2 of them. This one is smaller, but it still looks awful. It's super tedious. Perfect work for a computer to do. So let's pull back up our examples. This time, I'm not going to write it by hand. I'm just going to show you. You know what? I will write it by hand because I don't have that. I have CCSD, but I don't have CCD energy. And let me pull up a cheat sheet over here. So same thing. I need to tell Python where my library is. Which is right above me. I need to import pdaggerq. And then I need to grab an a-hat object from pdaggerq. And remember, I have to tell it what type of vacuum state I'm using. So I'm using the Fermi vacuum in this case. And now I want to set one other parameter that's relevant to couple cluster theory. If I go way up. Wow, really far. So, but back up here, starting with the Schrodinger equation, I argued that you get the energy from, you take the Schrodinger equation, you left multiply by e to the minus t, and you get the energy by left multiplying again by the reference configuration and integrating over all space. So this is a very specific bra state that you've applied, and by applying that bra state, you get the energy. There are different states that you could apply to get equations to solve for the amplitudes that show up in these t operators, because they're unknown quantities. So you can generate a system of equation to solve by using different, projecting onto different configurations here. So pdaggerq needs to know what the bra state is. So I'll scroll way back down, and then we'll tell pdaggerq what the bra state is. Man, you know what? I actually considered writing this all out live. What a terrible idea that would have been. Okay, so I have to say a hat dot set bra, and I want it to be the vacuum because it's the Hartree-Fock state. That's the vacuum state when you're working with a Fermi vacuum. And then I'll set the print level to 0 here. I'll set it to 1. Why not? So we'll see all the garbage that gets printed out. I'll make a nice pretty header because why not? And now I'm going to use a bunch of built-in functions that I've defined to make things easier. So if I go back to the GitHub, there's a whole bunch of notes here. Here's what I was talking about, the true vacuum versus the Fermi vacuum. And then there's a whole bunch of different built-in commands, so you don't have to set strings yourself. So you can say set strings of operator products using a function that's called add operator product. That's really small. Here, that's better. So I have add operator product, that'd be some constant. This is a 1 electron term, so this term by itself, this actually implies a sum over all PQ for this 1 electron term, H, the core Hamiltonian. This T1 implies a sum over all IA with T1 and the appropriate operators. And then this T2, again, implies a sum over all these labels, and it has that 1/4 built into it that needs to be there because of double counting. You don't have to define that. That's implied by this notation. And then you could go on and look at what all these things are. So T2 and T1 are these amplitudes, and so forth. There's also other cool functions like add commutator, so you could automatically have a term that does the commutator of H, P, Q, and T. And so you wouldn't have to write both terms. The code does it for you. You could have something do a double commutator for you. It won't keep track of a factor that should go with a double commutator, so you have to do that yourself. But that greatly simplifies what you need to do. So I have all the way up to quadruple commutators defined. So that makes things simpler, especially for what we're doing right now. So first things first, I want to do the 1 electron parts of the Hamiltonian, which is little h. So I have a hat dot add commutator. Remember this e to the minus t, h, e to the t, you define with that BCH expansion. So you have the operator itself, then commutators of the operator, and so forth. So I actually forgot the operator itself. So I just want h first, and that's add operator product with a factor of 1, and I want to call it HPQ. So P and Q are general labels to this code, so the code will automatically split P and Q into occupied and virtuals. It will use some internal naming scheme and then change them back to labels that you will understand at the end. Then the next term is the commutator. So I have add commutator of H and T2. And then I think that's it, because the energy, the BCH expansion truncates after just the single commutator. Let me check my cheat sheet to be sure. Oh, yeah, that's it, but I also need the 2 electron terms. So I use the notation G for the 2 electron part. I'm going to add an operator product that I'll call G. It's got 4 labels. Let's go back here. So this is actually an anti-symmetrized two-body operator, so it's slightly more complicated it's slightly different than what I put in my notes, but it's written in a slightly different way, but it's the same idea. If you actually care about that, I can talk to you offline. Okay, so I've added that operator product, and now I need to add the commutator of G and T2, and I'll do that. I'll steal this line. Okay, so that should be it. I have the 1 electron part and the 2 electron part. Those have been added. So each of these adds a different operator string and matrix elements as well, along with the factors we're defining, to a list of these strings. And then when I ask pdaggerq to rearrange them all, it's going to rearrange every term in the string, every term in the list of strings, and it'll try to cancel out terms that are the same so that you get a simple looking expression at the end. So I have a hat simplify, and now last time I just said print, and that's because I wanted all possible terms. Now I only want the fully contracted terms. Does the code also break down p and q into spatial orbitals, I alpha beta, in terms of alpha beta, or does the code assume all labels are spin orbital labels already? Yes and no. So the labels are what they are. If I wanted to do this in terms of spin orbital labels, if I wanted to add spin, I could explicitly add it, and then I would need to have terms for alpha alpha, alpha beta, beta beta, but I would just name them this way. So no, the code doesn't split it in terms of those itself, but you could do that. And then like each of these quantities it's not a character, it's a string, so it could be as many letters as you want it to be, if that makes sense. Super duper question. Okay, now print fully contracted. I only want the fully contracted terms because those are the only ones that are not 0, and that's it. Python, Ccd energy. What is happening? Add incompatible function arguments. Well, I don't know. Operator commutator is not even a thing, so I don't know what that thought it was. What is happening? 1 HPQ. Maybe it needs to be an ellip. Oh, it needs to be a... Sorry. These all have to be put in as lists. So everything except for the factor has to be inside square brackets. Sorry. I feel really unprepared for this demo. Good enough. Let's try that. Okay, great. So this is why I had set print level 0, because it prints out all of this stuff. So it's going to go and take every single string that was printed, that was input, and it's going to split them all into occupied and virtual terms, and it's going to print out every single starting term. This is a debug feature, so you can figure out what's wrong with the code you've written. Me. So if you remember, the first thing I put in there was the 1 electron contribution to the Hamiltonian. So there's a P and a Q. Both P and Q have to be split into occupied and virtual terms. So you get 4 terms just from that HPQ. You get general labels O1 and O2, general labels O1 and V2, V1 and O2, and V1 and V2. So that's all just the first term. And then everything after that is just as complicated. I have 4 terms for every term that we actually put in the input file. And then things get even uglier when you're dealing with the 2 electron terms. So this is anti-symmetrized 2 electron integral in physicist notation. Everything I was using in the notes was chemist notation. But the code internally uses physicist notation, anti-symmetrized integrals in physicist notation. So I have a sum over 4 labels PQRS. Every single one of those sums has to be split into occupied and virtual. So that's all done. It prints gazillions of lines of code. Well, that's not code. And then it prints out the beautiful, simple result. There's 3 terms. You have HII plus IJIJ, the 2-electron term, and then a contraction of your amplitudes with your 2-electron integrals with a factor of 1/4. Anybody who's a quantum chemist hanging out here, can you tell me what this first term is? HII plus IJIJ? This is even more awkward than waiting for an answer in class because there's a delay. So I don't even know how long I'm waiting. I'll have a sip of mystery liquid while we wait. Nothing? Nobody? Okay. The Hartree-Fock energy. Awesome. I'm going to call you Saki K90. Awesome, Saki K90. Yeah, that's the Hartree-Fock energy. So that's the Hartree-Fock energy, and then that's the correlation energy. So all of this just reduces to this really simple term. How fun. And that was way better than having to do all of those string manipulations by hand. If my student Nam is here, this is why I keep trying to get you to use this code rather than do everything by hand. Because this is so much easier than doing it by hand. Okay, I don't know if Nam's here. 13 people, how fun. Okay, I don't know what else I had here, so let's pull up my iPad. Oh! Okay, hey Nam. Good job on getting the Hartree-Fock energy. I'm very proud of you. Okay, where's my iPad? There it is. So, as I said, evaluating this whole thing is super tedious by hand, but it's perfect work for a computer. pdaggerq, Python demo. And that's all I have from my prepared notes. So, for the remainder of this, are you a fan of coffee jellies? Hello, everyone. I don't have anything else specific planned here. Basically, I was going to wing it from here on. I can show you guys how you can do more complicated things like the CCSD equations for the amplitudes as well. That might be worth showing. And then also there's some features that I wanted to add to the code, but I honestly don't know if I have that in me tonight. We can start that though. Okay, and then I'm going to play Super Mario Brothers 2. Or 1. I don't know. We'll see. Okay, so one more example. If I want also the Ccd Amplitude Equations. If you recall, the wave function is defined as e to the t hat 2 acting on size 0, and t2 is a sum over all these orbital labels. These are unknown quantities. I don't know what these are. So I can write down the energy in terms of these guys, but that's useless if I don't know how to define them. You can determine them from the projective solution of the Schrodinger equation just like you did the energy. Oh, I got a follow? All right. Thanks for the follow. Unruly Chuli fan. Okay, so if I start from the Schrodinger equation, I had h e to the t 2 0 is e to the t2 0. I left multiply both sides, so now I have my similarity transformed Hamiltonian, e hat e to the t2 0. The exponential goes away on the right hand side, so I just have e 0. Now I left multiplied by the reference configuration to get the energy last time. If I want to determine amplitudes, I can left multiply by a specific configuration. now I have the overlap of two different Slater determinants and a basis. I'm assuming my orbitals are orthogonal to each other, and if that's the case, then this overlap is going to be 0. And psi ijab is just a electronic configuration that's generated from the reference through this 2-electron operator. So this will give me an equation to solve for the, you can't see what I'm writing. This will give me an equation to solve for Tijab. It actually gives me O squared V squared equations, a whole bunch of coupled linear, nonlinear equations to solve. And I can generate, and yeah, I solve these and I can determine T2. And I can generate these equations using pdaggerq, using exactly the same code as we just used, but I have to tell the code that there's a different bra state, because this is not the reference configuration, it's the adjoint of this thing that I just wrote. So if I look at these samples, I'm just going to modify this other code that had single excitations in it and get rid of them. And then I'll explain everything that's here. T1, no T1. Okay. No quadruple commutator. Okay. So up to the top, I need to tell the code where pdagger lives. I'm using the Fermi vacuum, and now I'm setting my bra state as doubles. And that will use some specific labels. What is T2 here? T2 is a operator that defines excitations out of the Hartree-Fock reference configuration. So in couple cluster, you define a wave function as this exponential operator. Got it. Okay. Okay. So I want to solve these equations. So by saying doubles, that basically picks the bra state to be a doubly excited configuration. Internally, I think the code uses M, N, E, and F for that. I need to change that so that it's user specific, because it's not a good idea for me to steal labels from the user. Anyway, that's how it works. So by saying doubles, that's what I get. I'm going to set the print level to 0 here because it prints off an insane amount of data. And this is what ends up getting evaluated. You have your similarity transformed Hamiltonian acting on this ket, and then your bra state is this thing. It's basically the adjoint of this guy, but I'm using different labels instead of ij, a, and b. Again, you have to do the BCH expansion of the Hamiltonian, the similarity transformed Hamiltonian, which has 1 electron and 2 electron terms. It turns out if you're only involving T2, here both of these terms truncate at double commutators. Actually, I think the first one truncates at single commutators. Fun fact, if you include too many terms in this code, it doesn't matter. They're just all going to be 0. So it just does a lot of work to get a bunch of zeros. So I have add operator product, I have add commutator, add double commutator, and there's a 1/2 that goes with the BCH expansion for the double commutator. And then I have the same thing with my, I don't need up to quadruple because I don't have T1. If you have T1, you need up to quadruple. Well, do you? I don't even remember. Did I say quadruple? Okay. So anyway, you have the anti-symmetrized integrals, commutator of those with T2, and then the double commutator of the anti-symmetrized integrals with T2. I simplify everything and print only the fully contracted terms. And what do you get? Oops. There's also other print functions. What do you get? A whole bunch of terms. So the fully contracted terms, there's a bunch involving the 1 electron part of the Hamiltonian, there's a bunch involving the 2 electron part of the Hamiltonian, and some of them involve contractions between the amplitudes and the 2 electron integrals, and then there's this bare 2 electron integral term. If you look at this, so a lot of times people do Hartree-Fock theory in terms of an already normal ordered Hamiltonian. Everything I've been doing here is with the regular Hamiltonian, not normal ordered. So there's terms here that show up that you might not expect to be there. What is this? Why does the starting string have HF in the bra? Because the HF in the bra is the Fermi vacuum. So this is the vacuum state. These are the operators that generate the excited configuration out of the vacuum state. And then this is the vacuum state as the ket. Okay. Is it not the doubles? It is the doubles. That's what this whole operator is. So this entire thing is psi MNEF. It's MN, it's E dagger F dagger NM. Aha, you missed the operator. Yeah, so that's what that is. Yeah. Have fun. So anyway, if you go through and combine terms, you'll find this looks just like the couple cluster equations you might look up in a book, except that I have them written in terms of 1 and 2 electron terms with the bare core Hamiltonian. So there's going to be a term involving 2 electron integrals that goes with this guy. So I think that's actually this one. So this term plus this term looks like the Fock matrix contracted with T2. So my code's not smart enough to collect those into like terms. Ask a Scientist Gaming, did you get all that? Okay. Yeah, so pdaggerq, I write in C and C++. I don't know the difference because I'm not schooled in such things. So it's C/C++, and then there's just a Python interface with PyBind. Got it. Okay, so I guess the last thing I'll do, I still am not sure if I'm going to do explicit coding, but I can go through and show there's some really cool stuff here. In terms of the things I already showed you, there's these operator products, which is probably the most useful thing because it's flexible. You can add whatever you want as long as I've defined the operator for you. You have 1 and 2 electron integrals. There's general pairs of creation annihilation operators if you wanted to derive density matrix elements. So you could derive the pqth element of the 1 RDM with this one. You could define the PQRS element of the 2 RDM with this one. There's regular couple cluster theory. You have the T1 and T2 amplitudes. I don't have anything beyond doubles yet, but that would be regular CCSD ground state. You could do the CCSD is not a Hermitian theory, so there's left and right hand solutions. You could do the left hand problem. These are left hand amplitudes. There are also the left hand amplitudes that you have in equation of motion couple cluster. That is a way of doing excited state calculations at the couple cluster level of theory. So I have left and right Eom CC operators. Note the factor of a fourth is included in all of these things. There's commutators, double commutators, triple commutators, quadruple commutators. You can set the bra and the ket to be different functions. So just like solving, I've noticed many quantum mechanics using Mathematica for these sorts of calculations. Is there a reason that you've written a custom code here using lower languages? Reason number one is I don't know how to use Mathematica. And this all came out of a lot of simple tools I developed like this are just because I'm bored one day. So I just wanted to write a code that did operator string manipulation. Probably the first version of this I did in graduate school. And then I wrote this and it was like halfway useful. I didn't really use it for much, but then we've been doing some more bizarre couple cluster methods recently, and it's just way too complicated to derive things by hand. If you just want to implement CCSD, you can just look up equations. You don't need to derive anything yourself. And honestly, that's how I developed a lot of my first implementations. But now that we're doing stuff that's beyond where I can find equations, we have to generate them ourselves. And so this is a tool I developed. But I know there are other, the only one I can think of off the top of my head, I think Ed Valeev has a Mathematica code called secquant or something like that. Yeah, but it only does up to singles and doubles at this point. I have been swamped this semester, so I haven't been able to do much. I really want to extend this. So everything all these guys up here are like robust functions to add full operator strings and their sums, which is cool, but you might want more flexibility than that. So there's also lower level ways to interact with this. These strings can be specified manually using the following commands. Some of them don't work when Fermi vacuum's the choice of vacuum state, but whatever. And so you can set any general string involving the string of operators. You could add some tensor to that. And I've defined just 1 electron and 2 electron tensors, so these would be H and G. And then you could set T amplitudes to go with it. So you give the labels. You could set L amplitudes and so forth, R amplitudes, everything else, and set a factor. And then once you've set everything yourself, you say add new string. And then here's just usage. So this is the CCSD energy, which is very similar to what we did, but now it has singles as well. Are some of your students pen and paper theoreticians? I always wanted to do that, but didn't know where to start with computing dipole interactions more efficiently than particle mesh, Ewald, and MD. I will try to code this code if I can pip install. You can't pip install, but if you missed, I don't know if you were here at the beginning. All you need is you just say cmake dot and then make, and then it's done. It's really easy to install. Yeah, so yeah, most of my students do a lot of method development. CMake it is then. All of my students do a lot of method development. One that I was making fun of earlier, Nam, he's super awesome and he's derived a lot of really complicated equations by hand that he could have done easier using pdaggerq, but that's fine if he does it by hand because that means he actually knows what he's doing. So yeah, basically everyone in my group has to do pen and paper stuff. That's what I like to do. Pen and paper and then implement it. I like the software parts. Okay, I'll show a couple more examples of weird codes that we have. I actually don't have them here. Our group recently started doing couple cluster theory with electron-photon interactions, and so this code can actually generate equations for cavity QED couple cluster as well. I just haven't written the documentation for it, but you have just different classes of amplitudes that also include photon excitations. And so when you have the photon excitations, you have different types of creation and annihilation operators that obey different statistics because boson wave functions are symmetric rather than anti-symmetric with respect to exchange. But all that machinery up through single and double excitations is in place here. I can show you guys one other thing for to prove to you that we can do Eom Type Calculations. So there's Eom CCSD. This is all in the built-in examples that are here. There's Eom CCSD.d1 _d1.py, and this will generate the elements of the 1 RDM at the equation of motion couple cluster level of theory. And so this is a bit more complicated than anything I've shown you so far because it's this crazy expectation value of this 1 electron operator element that is defined with E, I mentioned a minute ago. So this thing similarity transformed, so you have to have the BCH expansion of this, and then you have the full left and right UMCC wave functions. So you can do that. Python's nice that you can just make lists of these operator strings. So pdaggerq knows what L0, L1, and L2 are. So I can just make lists of right and left-hand operators. And if I want to evaluate the occupied block, I just have to loop over the left and right eigenvectors, right and left operators, and add operator products, commutators of the operator with because this thing needs to be similarity transformed. So that should be an E. Let's commit something. commutator, double commutators, and so forth. And so that's all pretty straightforward. It's a little tedious, but it's pretty straightforward to do. It's done all with operator products. I have the double commutators built in. I don't know why I chose to do it with the operator product. But then you can see, so this generates the 4 unique blocks of the one RDM. So there's the occupied block, there's the virtual block, there's the occupied virtual, and the virtual occupied. It's so a couple clusters not Hermitian, so occupied virtual and virtual occupied are different. I feel like the representation of these products can be improved with implementing SymPy. I am the last person to claim that this code is optimally implemented. I got it to the point that it worked, and now it works. So you're welcome to do a pull request. Unruly Truly fan. Cool.